We finally get into imaginary numbers, so now we can completely solve any polynomial that we're faced with. So we're going to go back to chapter 1, and we have these lovely polynomials, and we have to go back to, oh, what's the highest degree? Is it one tail up, one tail down, two tails up, blah, blah, blah. Okay, let's just get right into it. So here we have a polynomial, and we'll call this example 1. What we expect you to know by now is to count the degrees. 1, 2, 3, 4, 5. So this is a 5th degree polynomial. So now in your head, here's your head, that's your brain. You guys have big brains. You should know that a 5th degree means one tail up, one tail down. And since they're all positive, it's going to start with a tail down, it's going to end with a tail up, and in between there could be as many as 5 roots. 1, 2, 3, 4, 5. So if you had to give yourself a quick visual, it could look like that. The only way to find out would be to solve it. So we can find the roots of this equation by setting each factor equal to 0. So we know that to find the roots, we would first say x plus 2 times x minus 2 times x minus 8 times x squared plus 9 would set equal to 0. Then we know in order for anything to multiply up to 0, there's a possibility of each factor could possibly be 0. So x plus 2 could equal 0, x minus 2 could be 0, x minus 8 could be 0, and x squared plus 9 could be 0. This is all review, but I'm just writing it out very, very slowly in case you missed anything. So this means that this polynomial crosses the x-axis at -2. It crosses it at 2. It crosses it at 8. And well, I got to do a little work here. This one's not that easy. I'm going to bring -9 over to here. I'm going to take the square root now, and I get plus or minus the square root of -9. Well, up till now, that was impossible for us to do. But it makes sense. I have 1, 2, 3, 4, 5 roots, and it's a 5th degree problem. But now we're going to learn about that we have 3 real roots and 2 imaginary roots. That's what we call taking the square root of a negative number, an imaginary number. Now before we get into the why and how, I'm going to come over to Desmos real quick. And on Desmos, I've graphed this, and you can see that over here I've graphed my equation, and that it does indeed have roots of -2, 2, and 8, but it only crosses the x-axis 3 times. Where are those other 2 roots? Well, this is such a huge graph that we can't even show you its minimum maximum. But it makes sense if there are 2 imaginary roots. How can imaginary roots cross a real axis? So let's look into what imaginary numbers are. We are going to take our imaginary numbers and represent them by the letter I. Shocking! I for imaginary. That's not that hard, really. So what is I? Mathematicians define I squared as -1. You also may hear a lot of people say, well, I then is the principal root or the square root of -1. Both are right, but the formal definition starts out here. Well, you see, imaginary numbers have been around longer than most of the stuff you're learning today anywhere else in school. It started with the Greeks, Hieron, who you might have learned about last year with the area of a triangle formula. He started it, and then pretty much any mathematician who's anybody has studied complex numbers. Raphael Bombelli, he was the one who took Hieron's and ran with the idea first. he was kind of like, yeah, imaginary numbers exist, and he was trying to tell everybody about them, but they were kind of looking at him going, yeah, whatever, buddy. Next guy to come along on the scene, I mean, there's a lot of guys in between, but this guy, Caspar Wessel, he said, well, these imaginary numbers can be graphed, and you'll learn how to graph imaginary numbers. So he was trying to tell everybody, yeah, they can be graphed. But the guys who really moved imaginary numbers, probably because they were respected mathematicians themselves, were Euler and Gauss. Euler came up with the I. Once he introduced that the imaginary numbers could be used by the letter I, more mathematicians began to run with it, and it was Carl Gauss who really came into the scene and started making imaginary numbers acceptable. Plenty of other mathematicians along the way who worked with complex numbers, but these four kind of helped move it a little further. But anyway, what is this? Well, the first thing you're going to learn about is a clock. So basically, anytime you invent something new in math, it has to hold to all the properties of math that you've ever learned. So you have to be able to use fractions, percents, add them, subtract them, divide them, multiply them, laws of exponents, blah, blah, blah. Everything that you've learned to date has to be done with I. So, for example, anything to the 0 power is 1. So that's how it starts. I to the 0 power is 1. Well, anything to the first power is itself. So I to the first power is I. And then here's where that definition came into play. I squared is negative 1. I cubed is negative I. So you may be saying, well, this is all well and good, but what does this mean? Well, basically, to try and sum up hundreds of years of math, this was an undoable problem. X squared equals negative 9 was impossible to do. So these mathematicians and many others decided that, well, if we can take the square root of a negative 9, if we broke it down into the square root of 9 times the square root of negative 1, well, we can take the square root of 9. It's 3. It's this square root of a negative 1 that was giving everybody issues. You can't take the square root of a negative 1. But they said, you know what? If we let the square root of negative 1 be a new number called I, we then can do everything in math that we could do with real numbers. And imaginary numbers led to nuclear energy and electricity. Don't ask me how. I'm not an engineer of either, but without these numbers, we wouldn't have that today. So the only way to really understand I is to start doing some problems. So for example, the square root of negative 36. You know it can't be 6 times 6 because that's positive 36. It can't be negative 6 times negative 6 because that's 36 also. And then the most popular answer that kids get is negative 6 times 6 is negative 36. But that's flawed reasoning because the definition of a square root means the numbers you use have to be the same. So mathematicians said, well, let's do this. Let's take the square root of 36 and factor out that square root of a negative 1 that's giving us issues. The square root of 36 is 6. And the square root of a negative 1 is I. There, the square root of negative 36 is 6 imaginary units. How about something that's not a perfect square? Still doable. We still have to hold on to our old rules of math, which means we look for the biggest perfect square that goes into 500, factor it out, and then once again there's that negative 1 that we got to take a square root of. Well, the square root of 100 is 10. I can't take the square root of 5, so it stays in the square root symbol, and the square root of negative 1 is I. There you go, that's what the square root of negative 500 is. 10 imaginary units times the square root of 5. How about a negative square root of negative 51? Well, there are no perfect squares that go into 51. I can't reduce it. All right, so I have the negative out front. I'll factor out 51. Break it off from the problem of square root of a negative 1. Well, I can't take the square root of 51, so it stays in a radical, but now we know the square root of a negative 1 is I. And like I said before, anytime you invent a new level of math, it has to apply to all the old rules. So I have to be able to add, subtract, multiply, and divide. Look how easy this is. the square root of negative 100. Well, hopefully by now you will see that this is very easy to do. Well, the square root of 100 is 10, and since there is a negative under the radical, it must be 10i. The square root of 81 is 9, and since there's a negative under the radical, it must be 9i. So 10 imaginary units plus 9 imaginary units give me 19 imaginary units altogether. Now, what's this circle? You're like, Mrs. Trillin, you wrote this on the other page too. Don't know why you wrote it in a circle. It's called the imaginary clock. And every answer in the imaginary world can be boiled down into one of these i's. So 3i to the 8th. I have 3 imaginary units raised to the 8th power. Well, I don't see I to the 8th here, but it's a clock. So you could just do this. You could start counting. Remember, we start counting with 1, not with 0. So 1, 2, 3, 4, 5, 6, 7, 8. In other words, I to the 8th power is the same as I to the 0, which is 1. So 3 times I raised to the 8th is the same as saying 3 times 1, which is 3. Now when we get big numbers like 99, please don't do this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 20. Oh my Lord. However, there's 2 ways to look at this. There's the brute way, force it in, get my answer, show me the mathematical way, I'll get it every time, or the elegant way that you understand. So in other words, if you noticed right here, these are all multiples of 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Get it? Well, I could look at this and I could say that this is I to the 100th power because that's a multiple of 4, which means I will end up here. But I don't want I to the 100th, I want I to the 99th. So it really must be I cubed. So I could look at this as 5 times I cubed, because that's the same answer, and then 5 times negative I, which means this answer is negative 5i. I could look at it also another way. I could divide out. I could say, well, there's only 4 answers it could be. So how many times would I go around the clock? 4 goes into 99. That's 2, that's 8, that's 19, that's 4, that's 16. Remainder 3. The remainder tells you what power you're at, the 3rd power, because this tells me I went around the clock 24 times, whoop, and then I went 1, 2, 3 more spots. Some people look at it as a fraction. Because we are calculator dependent, when you do 99 divided by 4 on your calculator, you get 24.75. Well, 75 means 3/4. So I went 3/4 of the way around the clock. I don't care how you look at it, just find one way you're comfortable with. And the last example, well, this isn't that hard. I've got I plus I squared plus I cubed plus I to the 4th. Well, I'm going to boil it all down into just the simplest way I can write I. Well, I is I squared is negative 1, I cubed is negative I, and I to the 4th is 1. Whoops, that's a plus sign. Ooh, look at this phenomenon. 0. The last thing we're going to look at real quick is what that guy Bombelli said. He said we could graph these imaginary numbers. Well, graphing imaginary numbers is very simple. Notice that when we go to graph imaginary numbers, we have two parts. We are going to call this the real part, and this the imaginary part, which brings us to the highest level of number known to math and man, a complex number. Can you see why it's complex? Because it's the combining of a real number and an imaginary number, which gives us a very complex number. But that being said, don't let that make this hard. If I were to ask you to graph the point 3, 2, you would think that's very easy. I would simply go over to 3, 2, 1, 2, 3, 1, 2, and put a point there. Hey, guess what? You just graphed the point 3 plus 2i, because all I'm going to do is not call this the I-axis, but call this the imaginary axis. So that, likewise, graphing the point -4, -3i means basically I have -4 as the real part and -3i as the imaginary part. I mean, do I really have to go through this? -8 plus 9i, we want you to read it as -8 is the real part, so I'll go to -8 on my real axis, and then I must go to +9 imaginary parts. Boom. So all you're doing is really looking at these as good old-fashioned points. And then 0 plus 7i, done.